So we have answered all our first set of questions in the algorithm. Next is, what does the system give to elements with integral causality? Okay. How many equations are we going to have? How many states do we have? How many storage elements do we have? How many I's and C's do we have? We have 3 I's and 2 C's. Okay. 2 C's corresponding to the couplings, stiffness of the couplings, and 3 I's corresponding to the engine, bogie A and bogie B. So totally we have 5 states, and so we will ask this question to 5 different. So first one is, what does this system give to this element? Effort of flow? Effort 1. You see, this element is receiving effort, so effort 1. So come here, it is rate of change of the momentum of the engine, effort 1. What is this effort 1? Effort 1 is effort 4 minus effort 5 minus effort 6. Effort 4 minus effort 5 minus effort 6. What is effort 4? Effort 4 has been defined earlier on line, on which line? Line 18. Okay. Effort 5 also has been defined on line 37 over here. Effort 6 has also been, no, effort 6 needs to be defined. So effort 6 is coming from where? Effort 6 is actually being brought by effort 7 in the zero junction. So effort 6 is the same as effort 7. And effort 7, what is it? Effort 7 is equal to effort 8 plus effort 9. So effort 7 is effort 8 plus effort 9. And effort 8 and effort 9 have both been defined here. Line 23 is effort 8 and line 29 is effort 9. So you have got all these efforts listed out. Okay. Then we ask the question to the next. What does our system give to this element, I element, with integral causality? What is it giving? Effort 2, which is rate of change of the momentum of bogie A. So dPA is equal to E2. E2 is equal to, what is it? Effort 10 minus effort 11. Effort 10 is here and effort 11 is here. Let us see effort 11. Effort 11 comes from effort 12. Effort 12 is equal to effort 13 plus effort 14. And effort 13 and effort 14 have both been defined earlier. You can see effort 14 and effort 13. Look at line 24 and line 34. Okay, they have both been defined earlier. Then effort 10. Effort 10 is the same as effort 7. And effort 7 also has been defined earlier on line 41. So this question is also answered. Then what does this system give to this element? Effort 3. Effort 3 is the rate of change of this momentum, dPb. What is it? It is coming from effort 15. Effort 15 is the same as effort 12. Effort 12 has already been worked out here on line 47, effort 13 plus effort 14, and you can trace it, you can trace its origin. So done. What does the system give to this? What does the system give to this C element? Flow. Flow is flow 8, which is Q dot dQ, dQAE. This flow 8 comes from flow 7. Flow 8 equal to flow 7. And what is flow 7? Flow 7 is equal to flow 6 minus flow 10. Flow 6 minus flow 10. What is flow 6? It has already been answered earlier. Okay, and flow 10 also has been answered earlier. It has been flow 6 and flow 10 have been answered earlier.
Flow 1, flow 2.
Flow 10 is here on line 27 and flow 6 here is on 27. So done. Then you have QAB, flow 13. Flow 13 is equal to flow 12. So flow 13 comes from flow 12. Flow 12 is equal to flow 11 minus flow 15. Flow 11 minus flow 15. Both flow 11 and flow 15 have been defined earlier, where
Flow 2 and flow 3.
flow 11 and 15 on line 31 and 32. Done. So we have got all the derivatives of the states, okay, and we can arrange them again in the same order in which they occur, and we provide a transpose of this. We send this out as the output of this function, which will be called again and again at every Runge-Kutta time of integration. So this is how we have completed our coding, and we are also going to see the plot results. So we'll have a few more lines of commands here, because we have a few more curves now. We are going to plot all of them. So let us now start with the simulation for this. Very fast. Okay. So the momentum of the engine, just initially there were some transients here. This is the momentum of the bogie A, it's also increasing. Momentum of bogie B. These are the momenta of the engine and the bogies, and you can see the momentum of the engine, it's given in this blue, and momentum of bogie A and B are almost sitting one on the other. So you are getting one line here like this. Now if you analyze the deformation of the couplings between the engine and the bogie, you initially started with a jerk, and so what has happened? Your system was initially at rest, but because of the jerk, the transients got excited, and that is what resulted in these transient oscillations. But because once the system pulled up and it became steady like this, and so your deformation, it remains steady thereafter. This is the deformation of the coupling with both A and B, and this is the relative deformation. Okay, you can see both these deformations have been placed here, and this looks wonderful. This is the phase diagram of the deformations. If you see the deformation of the two couplings, they are not in the same phase. They are not like this, same phase. They are, their phases are different. You can see that. Otherwise it would have been a straight line like this, just oscillating just like this. But that is not the case. It's going something like this. Okay. So there is, you can study the phase of this also. So this is as far as the deformation of the couplings is concerned. I think we have time for one quick simulation more, or would you like to ask questions? I have one more example. I can quickly show it to you, but I'll not explain the coding. I'll just show you the example. Yeah, so we have this example here, and here let us see this figure. Yeah. I think I'll have to explain its bond graph, but doesn't matter. I'm not going to explain the coding, so explaining the bond graph is okay. So in this system we have a fluid, mass fluid system you have two platforms here, M1 and M2, and the mass of this platform is M1, mass over here is M2. There is fluid here in this chamber. It's taken as a compressible fluid, and you have area A1, area of cross section of this section as A2, and we are applying forces F1 and F2 over here. So I am taking these velocities upwards as x1 dot, x2 dot. Now let's see how we model this using bond graph. So we start with our flow mapping approach. So we start with this mass motion of this mass 1. We apply the inertia of this, we place the inertia of this on this one junction. Then we also indicate the flow. I am not showing a source here. There is a reason why I have not done that, but anyway, let's say that this is F1. Now we are going from to the fluid. The relationship is one of flow to flow. So what is the element that you are going to have? The velocity of this is going to get connected to the volume flow rate of fluid. So this is going to be pressure here, and here you are going to have a transformer, and it is going to be related to this side. Okay, so this force is going to result in a pressure, and on this side you can also model the friction between the walls of this platform, of this chamber and this platform. Then we are putting a zero junction in order to represent the pressure over here, it's common. On the other side we have mass M2, exactly the same steps. We have R2, that is the friction of this platform. We have transformer here, and here the area of cross section here is A2, and we are taking the relative, difference in the volumes, okay, volume flow rates. These are volume flow rates Q1 and Q2 in these two sections, and that becomes modeled by a C element, and we are going to consider this as the C element is going to be for a fluid, it will involve the bulk modulus. So you are going to have initial volume divided by the bulk modulus. So that will be actually the K inverse part of this. I am not going into the depth of this, sorry. And if it is a gas, we could take it as the initial volume under standard conditions upon the initial density divided by the speed of sound square. So if it is to take a compressible gas into account, but let's take it as just a fluid in this case, and you can actually relate it to the decrease in the volume. So if we simulate this part, if we go back to MATLAB now and we take the first file, so again we are going to have our three files, and I am not going to explain these to you because I have already explained to you the bond graph model and we have just a couple of minutes, but you can see the files. There is the same structure that we have, okay, and we have finally the output derivatives, and then we can see also the plot file. And now I am going to simulate this. Done. Okay, so you can see that what were the initial conditions for this? You can see the initial conditions were, we provided an initial velocity